The plenary session is on photonics and metamaterials. That's why the final talk I have chosen the title as Photonics and Metamaterials. And I know that the audience is heterogeneous and mostly students. So I must put myself in front of the students and not in front of the experts. Experts will excuse me for this. Okay. So photonics and metamaterials. I believe 21st century will definitely be the century of photonics, as the 20th century was the century of electronics. Photonics is the science and technology of generating, controlling and detecting photons. We find photonics everywhere in consumer electronics, telecommunications, healthcare, manufacturing industry, defense and security, and finally in entertainment. Every new morning, photonics is opening up unknown, unheard of, and far-reaching possibilities limited only by the lack of our imagination. Metamaterials are also the watchword of 21st century. In the year 2000, first successful metamaterial was experimentally demonstrated in University of California at Santiago that could exhibit negative refractive index, unusual to our natural material where we have positive refractive index. Alright, the ray will go in the minus theta direction of the normal. This is a counterintuitive phenomenon not available in nature. Alright, that's why we term it as metamaterial, beyond nature. The Greek word meta means beyond. Initial developments of metamaterial was in the microwave frequency domain. We were happy in the initial domain because I am from microwaves and now starting to learn photonics. This was due to the fabrication technology, limitations of the fabrication technology. But with the advent of nano fabrication technology of today, the photonic metamaterial, that is metamaterial optical frequency, are now possible to fabricate, which opened up an excitingly new vista of applications of metamaterials in photonics. In my talk, there are two parts. Initially, I will talk of basics of metamaterials, including its exotic applications with which it started, like negative refractive index, cloaking, which is useful for stealth technology, and sub-wavelength imaging, and people are talking of super lens, and commonplace applications, which our students will be very much interested. They can do their BTech, MTech projects with these commonplace applications, like size miniaturized and efficient antennas, filters, and other passive components, including negative refractive index at microwave frequency. This will be the first part of my talk. And then I will go to photonic metamaterials and other metamaterial assisted photonic applications with astonishing and unprecedented capabilities, which is the work during last, say, few years, 5 to 10 years maximum, maybe for the last 5 years. I will cover these two aspects, alright. Initially, at microwave frequency. First question is, we are conversant with normal crystal, alright, normal material. Here, the wavelength is much larger than the lattice constant, alright. That means the distance between two atoms is much larger. Then, on the other side is photonic crystal, where wavelength is comparable to the lattice constant. Alright, these are two extremes. One is natural material, another is photonic crystals. And we peoples of metamaterial are in between. Lambda is greater than P, the lattice constant, maybe of the order of 10, and people are happy with, say, it is 1/6 or 1/8 and so on and so forth. Alright? So this is the domain of metamaterial. And that's why we call them as sub-wavelength structures. Alright? This diagram shows, this diagram shows the photonic crystals and non-crystal metamaterials. Our normal crystal and metamaterial both follow the effective medium. As Professor Ananta Ramakrishnan was telling, that it depends on the bulk property because it is effective medium, because the unit cells, because of this lambda greater than p, unit cells, the incident electromagnetic wave finds that as if it is a continuous medium, like the natural material. Alright? But when lambda is comparable to p in the photonic crystal domain, it's the Bragg condition that comes into play. And incidentally, let me mention, many people are confused or debate on photonic crystals. In photonic crystals also we have negative refraction, but not negative refractive index. This negative refraction is due to band edge Bragg diffraction. That means the ray will go in the other direction. But metamaterial is characterized by negative refractive index that is dependent on the two constitutive properties, the permittivity and permeability. And because it follows the effective medium theory, we call these are epsilon are effective and mu are effective. Alright, this is a bulk property. Metamaterial phenomenologically, this left-handed material is popularly known to make things invisible, like Harry Potter cloak. In some of the newspapers, sometimes I found that people are telling that metamaterials can make things invisible. Technically speaking, LHM or metamaterial is artificially structured material, commonly metal dielectric composites. Nowadays, not metal dielectric, but people are going with full dielectric. I'll talk about that. Having extrinsic inhomogeneity, but an incident electromagnetic wave, it is effectively homogeneous. Again, as Professor Ramakrishna mentioned, it has structural properties. That means how we place the unit cells in the periodic 3D structure, that determines its properties and not the chemistry of the material, whether it is made of copper or gold or silver. Alright? It is the structural properties which determines the LHM characteristics. These are realized in periodic structure, mimicking the lattice configuration of natural material. It is mimicking of that. And people are trying to approach as far as possible. And nowadays people are talking of quantum metamaterials, fashionable word, but people are talking about that, to make it really not only mimicking, but rather, if you permit me the word, replacing that. In recent years, the R&D in metamaterials is very attractive to realize exotic functionalities, and I find that in India, every new morning, new institutes are taking up metamaterial as their frontline research, and this is very interesting that in coming decade, probably India will be one of most important country to give best results on metamaterials to the world. We have such potential researchers. Now, why this is left-handed materials? Our normal material follows the right-handed triad EHK, alright, and phase velocity and group velocity carries the energy, are in the positive z direction. That is what is the intuitive one, the one we work with. But the counterintuitive one is that E, H and K forms the left-handed triad, and the K vector is in the minus z direction, but the energy vector or Vg vector should be in the positive direction, otherwise it will not follow causality, right? So this is left-handed material with left-handed triad and right-handed material, natural material with right-handed triad. Now, look at this picture. In the third quadrant, we have double negative material or metamaterial, where both epsilon and mu are negative, and the refracted ray goes on the other side of the normal. But in DPS, in the first quadrant, the refraction is the one we are familiar with. But in the other two, second and fourth quadrant, because epsilon or mu, either of them are negative, so signal will be reflected back. There cannot be any refraction. Alright. Who are the visionaries for this metamaterial? Definitely first, James Clerk Maxwell, the father figure of electromagnetics. His wave equation is really a unique one. It does not need relativistic correction, and also it does not need LHM correction. It is equally applicable for right-handed and left-handed materials, because in the wave equation, the refractive index appears as square power. Alright. And I must mention the name of Sir J.C. Bose from Calcutta. He was an experimental wizard. How thoughts came in his mind to do all these things, we can research upon that. But interestingly, his research on twisted structure in 1998, its polarizer, was essentially artificial chiral material we know in today's terminology, right? So, as visionaries, I must put J.C. Bose as one of the visionaries, because vision is something which gives you the spirit to think 100 years ahead of your time. And V.G. Vassalagho is again a great visionary, because he just thought, if I make permittivity and permeability negative, what happens? Let us see. So in his seminal paper in 1967, he found that while doing that, we can realize the reversibility of Snell's law, reverse Doppler effect, and reverse Cherenkov radiation for material epsilon and mu simultaneously negative. Then comes the gentleman John Penry, who made the real practical contribution. He showed that possibility for practically realizing the electric and magnetic plasma at micro frequency using an array of thin metallic wires in 1996, as Professor Ramakrishnan showed that, and an array of split ring resonators in 1999, respectively, to realize negative epsilon are effective and negative mu are effective below the plasma frequency. So, from 1999 onwards, the real journey of realizing metamaterials started. In 2000, the first plasmonic metamaterial was made. This was with thin wire array of this and SRR matrix, as it has been shown here, and it has been fashionably termed as electric atom and magnetic atom. Electric atoms and magnetic atoms, the split ring resonators. This is the first metamaterial. Then comes, so this plasmonic metamaterials, because they are resonant in nature, they cannot provide very broad bandwidth. So, in 2002, Aleph Harretz et al. Thought that how to make broadband structures. So, they started with transmission line metamaterial. Normal transmission line you have inductance and capacitance, the equivalent circuit. So this is a low pass filter. Just to reverse it, you interchange the position of capacitance and inductance, it becomes a high pass filter. So if you do a small exercise of telegrapher's equation and solve those equations with epsilon and mu with high pass characteristics, then you will find that your phase constant will be negative, your phase velocity will be negative, and refractive index will be negative. But Vg will definitely be positive. It has to be to maintain causality, right? So what they did, they made periodically loaded transmission lines. That means take the host transmission line and periodically load it with inductance and capacitance, but you have to maintain the subwavelength nature. That means P should be less than wave. Alright, this is what is the design criterion. So in 2002, this is the first periodically loaded transmission line metamaterial. It can give broadband. And now let me tell a few words about our humble research, a brief glimpse. This is the first metamaterial we made at Calcutta University in collaboration with Samir Kolkata Center and Bark Mumbai. And this was a labyrinth resonator and thin wire structure. We have given these characteristics here, and it shows that with a 15-degree prism of this metamaterial, we could realize analytically a refractive index of minus 1.84 at 31.25 GHz, and experimental result was N with minus 1.89 at 30.858 GHz. Our initial experimental arrangement was a crude one, as you can see. Do not laugh at it. In future, we have improved it and made it technically more viable. We have also worked with filter, bandpass filter, using this CRLH. This is combined right and left-handed structure of PLTL and H-coupled bandpass filter, and we have observed that with CRLH bandpass filter, insertion loss is 1.6 dB compared to 2.3 dB for H-coupled one, and harmonics suppressed up to 10 GHz for the metamaterial based one, but second and third harmonics are present in H-coupled filter. By the way, this work is by my BTech students. So, students present here can do these works. These are not very hi-fi things. We can do this in our own hand. No problem. Here is another example of student level. This is a patch antenna loaded with complementary split ring resonator. And this is again a BTech student project work I have taken from them. And you find that there is 24% size miniaturization, but with performance characteristics of both the normal patch and the CSRO loaded patch are pretty good. We have also worked with some variants of split ring resonators like multiple split ring resonator, then spiral resonator and labyrinth resonator, and we find that labyrinth resonator has much higher bandwidth compared to the other two structure, and its dimension is, physical dimension is also larger compared to other two structures. So for higher frequency design, we can tolerate better design tolerances for labyrinth structure. Alright. We have also tried with variants of split ring, this spiral resonator, two-turn spiral resonator and non-bianisotropic spiral resonator with improved characteristics. I'm not going into the details of that anymore. We have also worked with this wear media, which demands new formulation for its characterization. So we did it. Also, we have tried with 2D Cartware LR structure, and we have observed that now our experimental element is quite sophisticated, and we observed a negative refractive index of minus 1.68 with this structure. We have also worked with leaky wave antenna with metamaterial, and here we find that we can make electronic beam steering not only in the first quadrant, also in the second quadrant, all right. So this gives you much better electronic beam steering, which will be useful for phased array radar. Now we come to exotic applications of exotic potential of metamaterial like super lens or sub-wavelength imaging. It says it can get over the diffraction limit and it can realize evanescent wave growth. Look, we cannot get into any resolution below wavelength because we cannot harness the evanescent waves. All right. What we do with is the propagating wave. Evanescent wave decays very fast. But if we can do something that we can take the evanescent wave from object point to image point by some means, which this metamaterial can do with evanescent wave growth process, then we can get the sub-wavelength details of the object, which is a very, very great thing which this metamaterial people are trying to realize. But as Professor Ramakrishna mentioned, the loss in the metamaterial design is the primary issue. So if we can have much low loss, then that will be more realizable. But it demands that it can which might one day make it possible to image individual strands of DNA if we can go to sub-wavelength imaging. Cloaking may not be of Harry Potter type, but we can have cloaking of micro objects these days, and also reverse Cherenkov radiation, which will be helpful in the design of future detectors for accelerator design. And here are the few words about what I was talking about, that this is the evanescent wave growth, how it takes place with surface plasmon polariton waves that helps in the process. I am not going to the details of that. So these are some of the super lens and sub-wavelength imaging techniques people have really realized. And this is about cloaking. The first picture shows, in simple terms, in the first picture it shows, look, how something is visible, because there is some incident ray, there is some reflected ray, there is some transmitted ray, and maybe there is some absorption. But if by some means we can get over the problem of reflected ray, we can get over the transmitted ray, and suppose there is no absorption, if the electromagnetic wave just glides past the object, all right, then the object cannot be seen. All right, this is what is shown here pictorially. Just to give an example, when there is a stream and you have big boulders, there is splashing of water on all sides. But if there are small pebbles in the stream of water, you do not feel any turbulence, all right? But the object is there. But for an observer, the object is not visible. This is how we make things invisible with metamaterial. We do not make it magic to be absent there, it is present there, but by manipulating the refractive index, we can realize that zero reflection, zero absorption, zero transmission. Alright. So people have worked with this with microwave structure, optical structure. I am not going to the details because time will not permit. This is reverse Cherenkov radiation. This Argonon lab is working on. But following them, we have worked with something interesting. Again, for student project, it will be interesting. You take a rectangular waveguide, load it with strips of SRR matrix, alright, and the electromagnetic wave will have interesting property of having stop band in the propagation band and propagation band in the stop band of normal waveguide. So you can design very sharp notch filters, alright. This can be a student project. In fact, my students have worked on that. Metamaterial application for absorbers. Our expert has spoken about that. I should not take any courage to talk about it anymore. Now comes photonic metamaterials. Now we are trying to bridge metamaterials with photonics. When we go to photonic level, beyond 200 terahertz, our normal wear structure and split ring structure will not work, because beyond 200 terahertz, metal does not behave anymore as a conductor and becomes transparent to the radiation for wavelength more shorter than 1.5 micrometer. So what is the solution at optical frequencies? What people have done? It is either with cut wire or fishnet. They wear nano wear structures. All right. What they do? Okay. This is for megahertz to terahertz. What they do? They use either the cut wire structure or fishnet structure, and with fishnet structure, they could realize 3D optical fishnet metamaterial at 1200 nanometer with a refractive index of 1.23. Alright. Now we go to metamaterial and photonic developments. These developments are for the last few years only. Alright. A totally new direction is coming up in metamaterial applications in photonics. In the early days of metamaterial research, metamaterial was considered to be with tolerable permittivity and permeability. But later on, people are talking about metamaterial fuel lasing spacer, metamaterial based carbon nanotube, and transparent metamaterial. In lasing spacer, what they do is this. The lasing spacer, identical plasmonic resonators, the split ring resonators, impose the frequency at which the device will lase, drawing energy from a supporting gain substrate. This combination of artificial classical electromagnetic resonators plays the role of the active medium in the lasing spacer, just as an assembly of essentially quantum inversely populated atoms plays as the same role in the conventional laser. The lasing spacer is the direction of emission is normal to the plane of the array, where the strong trap mode currents in the plasmonic resonators will oscillate in phase. So lasing spacer is becoming very important, because with metamolecules you can control its performance, you can control its bandwidth, and so on and so forth. Very hot topic of research these days. And on normal carbon nanotube, if you have metamaterial coating, you can have an order of magnitude improvement in its nonlinearity, as Professor Ramakrishna was telling, that you can have much better optical switches using this metamaterial based carbon nanotubes. And finally, the transparent metamaterial. This is the latest one people are talking about. Do not use metal, so there will be no loss as such, and also you can talk about single photon sources. All right. Let me tell, the innovation in transparent metamaterial lies in modifying the phenomenon of total internal reflection. Look, in this diagram we find that within the core material, energy is less, and in the cladding, energy is more carried by the evanescent wave. But with metamaterial coating, with this maneuvering, what you can do, you can confine the energy in the core material and you can reduce the energy in the evanescent wave in the cladding. Result is that you will have much better confinement of energy in the core and not in the cladding. Advantage is when you make photonic integration, then device to device coupling will be much reduced. That is what is important with this transparent metamaterial. It is made of all dielectric, no material, so no loss, so your input power required will be less. Why we need this? Quantum information technologies such as quantum cryptography, quantum information storage, and optical quantum computing demand effective stable sources of single photons and the nanostructure to control the quantum dynamics of these photons. And with this transparent metamaterial, 2016 report says, this is the latest one, that we can have broadband single photon sources with this transparent metamaterial, which will definitely revolutionize the photonic integration, where because this transparent metamaterial will be on dielectric or silicon substrate, so electronics and photonics can be integrated together with very less crosstalk. So future is very bright with photonics metamaterial. Finally, yes, I should not miss this opportunity to conclude. Miles to go before I slip. Right? Robert Frost. Can anyone tell me the 4 lines? Okay. Woods are lovely, dark and deep, but I have promises to keep. Miles to go before I sleep. Miles to go before I sleep. So whatever work we have done is just the beginning. We have to go a long way. Our journey will not stop. We'll make our journey with all our energy and strength. Right? Thank you.